For the invitation to talk here. It's my first time in India, so it's very interesting for me. Yeah, this talk is about two projects with people from Mainz, Paris, and Berlin, and from Potsdam and Berlin. And yeah, I try to combine these two different projects under the joint umbrella of hidden symmetries. So what do I mean by this? I guess everybody agrees that symmetries are crucial in physics, and if you want to compute something, you should rather first exploit all the symmetries you know in order not to have to do too much work. For instance, in QFT, the symmetries can constrain your particle content, the interactions, and also the form of your observables. However, not all the symmetries are so obvious from the start, and sometimes you have hidden symmetries. And yeah, just to give a very simple example of what I mean, let me mention the Kepler problem, where as an obvious symmetry you have the conservation of angular momentum, which restricts your motion to a plane. But on the other hand, you observe that there is no precession of the perihelion, and it's maybe not so obvious from the start. If you don't know the problem from your studies, it's not so easy to see what's the symmetry behind this. And in this case, it's the conserved Laplace-Runge lens vector, and it's so hidden that it seems that from time to time people have to rediscover it. Maybe not even knowing from people who studied this before, and this is actually only my very Eurocentric point of view, and I guess one would have to add other names from different continents as well. Of course.
So the difference between obvious and hidden is somewhat subjective. I mean, if somebody knew
Sure.
that to write the Kepler problem in parabolic coordinates to begin
Yes.
with, then they would have discovered this approximately. Then it would have been
Yes. This is a very soft definition of the word hidden, yes. It's subjective, yes. Of course, this talk is not about the Kepler problem, but rather about quantum field theory. So let's start with a rather obvious symmetry in quantum field theory, namely conformal symmetry of Yang-Mills theory, where the action can be seen to be invariant under conformal transformations. And an interesting quantity to investigate in this context are scattering amplitudes, amplitudes of gluons, which generically depend on colors, polarization vectors, and momenta. And conveniently, one can completely strip off this color structure here, which simply enters in form of this trace over the color generator, so that one ends up with a purely kinematic part depending only on momenta and polarization vectors. Then one useful thing to do is to trade also these momenta and polarization vectors for momentum spinors lambda and lambda bar and helicities, because these momentum spinors, SU2 spinors lambda and lambda bar, explicitly solve this masslessness constraints of the external gluons. And then one can sit down, write down a representation of the conformal algebra via these differential operators in these SU2 spinors here. So we have momentum, the momentum generator, the dilatation generator, Lorentz generator, and special conformal generator. And all of these can be seen to annihilate this kinematical part of this gluon amplitude. So I actually want to go a step further and embed this into a larger context, namely into n equals 4 super Yang-Mills theory, which, as you know very well, is interesting for a number of reasons. It's believed to be dual to string theory on ADS 5 times S5. It has an even larger symmetry algebra, namely PSU2,2/4, and the symmetry is also preserved at the quantum level, since the beta function vanishes. And moreover, in the Toft limit, in the limit of an infinite number of colors with fixed Toft coupling here, the theory is believed to be integrable. If I want to look at scattering in this theory, I have to deal with all of these on-shell scattering states, gluons, fermions, and scalars. Yes? Sorry, it should also be dual to gravity without taking this one. Okay. Well, at the moment, yeah, I will be mainly interested in the gauge theory, on the gauge theory side, actually. My statements about gravity in the end will be also related to the field theory, to Einstein gravity, so not so much about ADS and this duality. This is mainly to motivate the considerations I want to make here. But yeah, maybe we can discuss this also later. So I'm now interested in scattering in this field theory where I have these on-shell states here, so no gravity at all, and I want to package these into a super field using such SU4 spinors, Grassmann valued SU4 spinors eta, and doing so the different powers of these Grassmann spinors measure the helicity of the respective particles. So this is just a convenient way to package my on-shell states. And then the scattering amplitude in this theory is a superspace function, a function of these on-shell fields, and in fact the tree-level gluon amplitudes agree with those in the Yang-Mills theory. So how does this amplitude look like? In addition to the standard overall momentum delta function, I have such a super overall momentum delta function, and then I have some function depending on the spinors lambda, lambda bar, and these SU4 spinors eta. And again, I can sit down, write down a representation of PSU2,2/4 in terms of these generators here. So here I have the conformal subalgebra, QQ bar and SS bar are the supercharges, and the SU4 symmetry, and these are all differential operators in these variables, and one can act with them on the tree-level amplitudes and find that they are annihilated. Sorry? Eta was this SU4 spinor that I used to package the fields in my superfield. So this is basically the analog of what I did in the Yang-Mills theory. The amplitudes inherit the symmetry of the Lagrangian. So that's not surprising. A more surprising thing is that you can introduce such dual variables, so-called region momenta, by this relation here. So this is simply the momentum pi, and then I find this xi via this relation, so xi minus xi plus 1 should equal the ith momentum. And I do the same for these super variables here. And then I can again write down a representation in terms of differential operators of this PSU2,2/4 algebra. And all of these here are simply local operators now just written in these variables. And again, these will annihilate the scattering amplitude. And this is not simply a rewriting of the original symmetry in a different language, which can be seen from the fact that both of these are local operators. So each of these only acts on one of the external particles at the same time, and the same here. But this transformation between them is actually non-local. So you see that there's something more than this original PSU2,2/4 symmetry. And in this ADS-CFT picture, the explanation can actually be given by a duality to Wilson loops, Wilson loops which have the cusps exactly at these positions xi here. So,
Here, by here, do you mean AN or A4? When you write PSP 2,1, 2,4?
Here I mean PS2,4, and here I mean AN. AN means the endpoint amplitude.
But xi can be like.
I runs from 1 to n.
Then xi. So, but then say.
It's periodic.
But the symmetry is in the xi variables, right?
There's a symmetry in the xi variables, which is this one, and there's a symmetry in the original variables, which is this one.
So you can just explain I is the label of the external leg.
Right.
I is the label of the external leg, and how to get to 4 here, which is a number of generators. No, that's the symmetry of the original theory.
Yes, but there's an original one and there's a dual symmetry. These generators generate the same algebra, but in different variables. No? Yeah.
So I'm just asking, was it needed to be same algebra, or it could have been different, or it just stands off with the same algebra?
It was not needed to be a symmetry at all. It's a priori it's surprising, of course, if you see the picture behind, if later you understand where this comes from, namely from the duality to these Wilson loops, it's clearer that it should be the same symmetry. But in general, well, this is what I would call a hidden symmetry from the start, because it's not what I would expect from the Lagrangian. Yeah.
How this comes about? How to understand it from gravity? Or in another way?
How to understand this from gravity?
Not
Okay.
necessarily gravity, but just how to. You said that this now we understand.
No. I don't want to say that this was a proper explanation. I just want to say there is a picture behind. The talk is not about this. People like Maldacena and Alde have computed. Yes, in principle it's related to.
Many, because that is a property of the string theory. So does that mean generic CFT which admits a ADS dual duality would admit some form of dual symmetry?
Okay, the important thing is that the T-duality maps the theory to itself, right? So it's a.
Okay.
I don't think in general it's clear. For ABJM, people find similar symmetries on, for example, amplitudes, but it's not really clear how to formulate this in terms of T-duality. It's not clear that it's not possible, but there are problems. It doesn't work in the standard expected way, apparently.
Hello, can I just say something?
Yes.
Hello?
You stay.
Can you hear me?
Yes.
Yes?
Okay. Yeah, so my understanding was that this is formulaic T-duality, right? Not regular T-duality on string theory side.
I didn't
For
understand.
conformal symmetry, for the mapping to the string theory side, isn't it something like formulaic T-duality?
I guess I did not really understand.
So he's saying that when you translate to the string theory side,
Yes?
then it's not a normal T-duality. It's formulaic.
Yes, right.
Yeah, and that need not be a property of all string theories, right? And all string maps.
Okay, sure. Mm-hmm.
It's unlike T-duality, which is more universal.
Mm-hmm. Yeah. Right. You need fermionic T-duality. You have to include the whole algebra.
I think you can statement up to some order roughly. The statement is invariant.
Now this slide is just on tree-level amplitudes at the moment. Yeah.
Oh, fine.
If you, and this is also partly what this talk is about. If you go to loops, you will get singularities. You have to introduce a regulator that breaks conformal symmetry. Okay.
Tree level at finite dimension. He does not.
at tree level, it actually doesn't matter if you are in the planar limit. You only have single trace contributions.
Well, you need to be able to order the operator, which you would be able to use.
Okay, yeah, but this is due to the color trace, right, that I've stripped off.
Are there examples where there is a dual conformal symmetry but the different group?
ABJM, where it's OSP6/4. Yes. Sorry?
So what is the group and ABJM?
OSP6/4 is, but again, that's not understood how to formulate this as a T-duality, self-T-duality. Okay. The point of this was just to introduce the topic. So a natural question is, what happens if I combine these two algebras, right? Now, at the moment, I have two separate algebras in different variables. And what happens, for example, if I commute two of these generators, one from the first and one from the second algebra? And the answer is that you generate the so-called Yangian algebra, which is well known from integrability, which is an infinite dimensional algebra and an extension of an ordinary Lie algebra. And it analyzes so-called rational integrable models. And yeah, actually, I will in the lectures in the next days give a very basic introduction to this symmetry algebra. So let me here just briefly state what this Yangian is and how it's defined. It's generated by two different sets of generators, these level 0 generators JA and level 1 generators J hat A. The level 0 generators are simply the Lie algebra generators. They have a standard local tensor product action. So on my amplitudes, this K will run over all the external legs, for example, and they obey the standard Lie algebra commutation relations. These level 1 generators are more complicated. They have such a bilocal tensor product action or bilocal coproduct. So you take a density of this Lie algebra generators at position J and one at position K, and you sum over all relative positions, and you contract the two with the Lie algebra structure constant. And also these obey similar commutation relations as the Lie algebra generators. You have additional Serre relations, but that constrain these representations here. But for this talk, they will not be so important. I will make some more statements on this in the lectures. Yeah.
Why do they do so? Where are the dual generators?
It's not obvious how to get this. What you have to do is you write down the dual generators. You have to translate them into the original coordinates. And in principle, up to some subtleties, what you find is that in the original coordinates, they are now non-local, and they turn into something like this. Yeah?
Sorry, but the level 1 generator is certainly not a subalgebra.
No.
So how can I at least find this? I mean, from this structure, I looked at it a bit, but this thing that puzzles me is that apart from the level 0 generators, it's very difficult to see even a subalgebra after this.
What?
Should be isomorphic to these points /4, right? Which are the dual ones. So where do these live? Where do these generators live in this structure?
The dual ones, you mean?
Even roughly. Because here there is a property that the levels are additive under commutation, right?
Mm-hmm.
So it's difficult to see how they live.
Yeah, the translation is very subtle, actually. I mean, first you start with these dual generators. You have them in the x and theta variables.
But at the end of the day, they just live somewhere in this right level 0, level 1, level 2.
They live somewhere, yes. But yeah,
Is this been answered in the literature, or that also is not for there? So you mean in the level 1, are the all generators are dual generators or not? That's your question.
No, it's not that simple. No. Some of the generators turn into these level 1 generators.
What I'm going to argue is that, when you have a level 1, I can make a level 2. So level 2 has to be in some other. Then I can make a level 3, and that has to be in some other. How am I going to get closed finite dimension subalgebra?
Well, sure, yeah. Well, I mean, that's the interesting thing about the Yangian, that it's infinite dimensional, right?
But subalgebra, there should be a finite dimensional subalgebra corresponding to the dual.
I guess first you have to say on which space do these quantities act. Before I had this ordinary PSU 2,2/4 generators acting on lambda, bar, and eta. I have the dual ones acting on x and theta. To combine them, I have to blow both of them up to act on the whole space of all variables. So it's
But you at least agree that there has to be an algebraic answer.
You mean for every individual dual conformal generator, I should answer what it maps to in the Yangian.
Yeah.
Yes, I think one can do this, but I think one has to do it individually for the different generators. Yeah.
Linear combination, right? So the original
Okay.
you need everything.
Okay.
Only linear combinations are possible.
Okay.
Okay, yeah. The point here is that I have only two different sets of generators, which are both finite, but still this algebra is infinite dimensional, because if I commute, for example, two of these level 1 generators, I get a level 2 generator and so on. So I really generate an infinite dimensional algebra. And this symmetry has been identified for various different quantities in n=4 supermills theory. It's not that easy that you just go to the action, find it there, and translate it to observables. That's what people try to do now in the recent past, but it's a very tricky issue. So this Yangian symmetry has been found as a symmetry of the dilatation operator, scattering amplitudes, Wilson loops. And as I said, recently people try to formulate it also on the action, but that's very much work in progress.
So, it's a two-conformal symmetry. When you created the Yangian, just by trying to find finite dimensional subsets of the Yangian, would not that be the full, like, it's like gives you a classification of dual symmetries, right? It's a set of finite dimensional subsets of the Yangian. Is that true? Some magician came and told me all the finite dimensional subsets.
Again, I don't think this translation from the dual symmetry to the Yangian is this. I think it's very subtle, and one really has to do it generator by generator, and they translate to different.
It's complicated, but suppose I have the.
But then I don't translate that. The observation here is that there is this symmetry that you know, and then there is it just happens to be that the answer is dual to the component also. And together they make up this symmetry.
But we wrote down the Yangian just from using the non-dual generator, right? So somewhere in this infinite dimensional algebra, there's a finite dimensional subalgebra. It happens to be the dual symmetry. Now, are there like if I found another finite dimensional subalgebra of the Yangian, yeah, you already have two PSU 2, 2, 4. Suppose there's a third one. Suppose there's a third finite dimensional subalgebra. Is it are there further constraints on like could there be a theory where the dual symmetry is that third algebra? There is a non-dual symmetry we want to keep it with. Like other, would it be case that all finite dimensional subalgebras of the Yangian are potential dual?
Why are you interested in doing finite dimension? This is the whole structure. So once you understand this is the whole structure that you want to work with. You don't need to go back again to the whole look for finite dimension.
But probably what he's asking, so I started with one of the PSU that group and constructed infinite dimension. I could have started with some other one, and I could have constructed the same. And one can show probably they are one-to-one related, right? They are equivalent.
Yes, you could also construct it over this dual conformal symmetry. Yes.
But is it right? What the good way to ask what I was asking is so we take the case where the dual and the non-dual look at it. Okay, in terms of the Yangian, you get perfect dual Yangian.
I would say this ordinary and dual conformal symmetry is very special to the ADS-CFT duality.
Okay.
Whereas the Yangian is more general. You can have it for other integrable models. So it's not clear that every Yangian symmetry can be formulated in terms of an ordinary and dual. Yeah.
Like I'm talking about the case where there is a dual symmetry. So like you gave that the
Mhm.
dual and the non-dual are different groups, right?
They're not different. They are both OSP6/4.
Oh, right. But is there an example where dual and non-dual are different groups?
No.
No. Okay. Then I will look at it.
Actually, I guess these are the only examples that we have anyway. So, yeah.
So you said there are only two examples. N is equal to 6 and N is equal to 4. Or there was 6 to 3 and N equals 4 to 4. Is that only two that is known? You know?
Yes, I think of this ordinary.
Yeah, N is equal to 3D has some of this symmetry, at least some.
Okay.
That's fundamental. Not the adjoint does not have that symmetry, but
Mhm.
fundamental.
It has the dual conformal symmetry.
Yeah.
Okay, so you also find the
Yeah.
Yangian there? Oh, okay, maybe we can
That's
discuss.
yeah, that is at the 4-point level. Also, here you're saying you have.
You're talking about the 4-point amplitude now, or?
Probably I can tell you this later after this. But
I guess maybe I know the paper even. Yeah. Okay. Yeah, maybe we discuss afterwards.
So here everything you constructed out of the on-cell things, right? Till now,
Yeah.
based on scattering amplitude.
Yes. I mean, this slide is very general. You can do other things.
So the point is, if I can show the axial thing, which is off-cell thing, all the rest follows, or?
It's really not clear. This is the group of Niklas Beisert who has been working on this already for some years now, and they have a few papers, but only to find what the right criterion on the action is not easy at all, because yeah, you have a 4-dimensional theory, you have these generators which are defined naturally on a 2-dimensional on a 1-dimensional lattice in principle. So yeah, then you have many problems with gauge symmetry. Only to properly formulate the problem on the level of the action is difficult. And then there are now some new approaches to try to take this over to Ward identities for correlation functions. But yeah, this is really very much in progress.
When you talk about the Ward identities for correlation functions, you're referring to the latest paper by the
Yes. Right, which is came out very recently.
So these all correspond to local symmetries, all these generators, the infinite number of.
Well, no, these are non-local, right? Or if you
Meaning that in some other variables, do they correspond to locally observed currents? I mean, since one is talking about action, principle and what are they taking as well?
okay, maybe one should rather understand them there as the symmetries of the equations of motion. No, still I don't think they are local. The point is they are always non-local on the color trace. Yeah. So this is the important thing, how this one dimension enters in n equals 4. You have this color trace also in the action, and on this color trace they are always non-local, so they always act in this particular way.
I was just wondering,
It's not understood how to formulate this properly as on the level of the action, then to derive it as a Noether symmetry. It's not.
that's what I mean.
Yeah. But even in 2D, this is not well understood. On this I will tell more in the lectures also. Okay. So let's go back to the amplitudes. What does this Yangian now mean on the amplitude? Again, I have this color trace here, and as I already said, this color trace is important to actually write down the level of the the action of the level 1 generator, because it has this bilocal coproduct. But then again, these generators are differential operators. One can act with them on the amplitude, and one finds invariance, and actually one can even argue that this symmetry completely fixes the tree-level S matrix of n equals 4 supermills theory. Just a side comment, well, if one knows this Kuhlmann-Mandula and Haag-Lopez-Chansky-Sonius theorems, there people say that the S matrix in D greater than 2 dimensions can only have Poincaré plus an internal or supersymmetry. And the point why this is not in contradiction to this theorem is that the level 1 generators actually have this non-local coproduct, this non-local action on the tensor product, and this is a hidden assumption in the proof of the theorem that the generators should just have a local coproduct. So this is actually not forbidden as a symmetry of a 4-dimensional S matrix. So what I told you so far was just about tree level, and a natural question is whether one can lift this to loop amplitudes. And I actually want to spend the rest of this talk on 2 different questions. And the first one addresses exactly this, whether one can define a particular sector of this n equals 4 supermills theory where one lifts this symmetry to loop amplitudes. Generically in n equals 4, the problem is if you go to loops, you get singularities that you have to regulate, breaking the conformal symmetry, so your nice picture somehow breaks down. So is there a sector where one can still lift this to loops? And then in the second part, I want to come to a slightly different topic, namely to the question of similar structures could also survive in a theory of gravity, of standard Einstein gravity in flat space. And the question I want to address there is simply whether there could be conformal symmetry of these scattering amplitudes. But this in the second part. So let me come to this first part. So I want to go back to n equals 4 supermills theory, which is defined schematically by this Lagrangian here. And I want to introduce now further parameters by making the product in Lagrangian to fields x times y non-commutative. And I introduce such a twist function. Here the q's are the asymmetry Cartan charges. And importantly, I introduce, by doing this, 3 different parameters, gamma a, where a runs from 1 to 3. The supersymmetry in this theory, on the one hand, you could say, okay, it's broken, but probably it's more correct to say that it becomes twisted. For instance, on the scattering amplitudes, you already see this twist by writing this gamma deformed amplitudes as such a bilocal twist factor times the original amplitudes. So doing this, you introduce some twist with new parameters gamma a. And for the purpose of this talk, this is interesting because these parameters gamma a can now be used to play with. So I can take particular limits in these parameters and maybe project out certain fields to modify the theory. And I'm particularly interested in a certain double scaling limit that was introduced by these people here in 2015. And this limit consists of taking the weak Toft coupling and at the same time taking these parameters here, gamma a, to imaginary infinity. And I want to keep this particular product here, g times e to the gamma a fixed, and this psi will then be my new coupling constant. And I can actually do this in different ways. I can take only one of these parameters to I infinity, all 3 or 2 of them. So I have different ways to take this limit, and I thereby project out certain fields of my theory, which decouple in this limit. Yeah. In particular, I have no more gluons. So let's look at a very particular case of this limit. I take n equals 4 supermills theory with its Lagrangian. I introduce these 3 parameters. And now I take only this gamma 3 to I infinity. And the coupling, Toft coupling to 0. And I keep this fixed, which gives me a new coupling constant psi. And it turns out that almost all of the fields decouple, and I end up with a Lagrangian, including only 2 complex scalar fields, phi 1 and phi 2. So this is the resulting Lagrangian. And I have a single 4-point vertex of these scalar fields.
And why are there only 3 gammas?
Why? Well, at the start there are these 3 gammas because I can introduce this deformation.
Yeah.
I have 3 Cartan charges which I can use to. Mhm.
Because if you related to the fact that 3 parallel fields
Mhm. So, taking this particular limit, starting from my planar n equals 4, I get this Lagrangian. And this will be the theory I'm now interested in. Unfortunately, it's a non-unitary theory, so from a physicist's point of view, you might ask, okay, why should I actually look at this? Why is this interesting? It's non-unitary because I have only this ordered 4-point vertex and not its complex conjugate. You keep the complex conjugate. You keep the complex conjugate vertex and you drop this one. So, yeah. It's G to infinity? Ah.
You are taking G to 0 and gamma 3 to I infinity. If you take gamma 3 to minus I infinity, if you take gamma to go to minus I infinity,
Yes.
then the corresponding thing that you are taking is that it implies G goes to infinity. The gravity side. This takes two coupling to 0.
Yes, yes, yes.
No interaction. On the other side, you can take G to infinity and gamma 3 to minus I infinity.
I don't know if one can make sense of this. I mean,
But if the
how you take this? Yeah.
blue ones would still be coupled strongly.
Yes.
They will be strongly coupled. It should travel to
I don't know. Yeah. Okay, this is a non-unitary theory, so a priori maybe not so interesting. And the interest, at least from my point of view, arises when you consider such single trace correlators. So you take a product of these fields, these 4 scalars here, and you look at the correlation function. And because you have only this single ordered 4-point vertex, you can actually argue that there's a single Feynman graph that corresponds to this correlator. So you have a correspondence between correlators and individual Feynman graphs now. Yeah, and this is interesting because in n equals 4, people usually make interesting statements like from integrability about correlation functions, or scattering amplitudes, as I motivated in the first part. And now this, if one can really go through this procedure here smoothly, these individual Feynman integrals should somehow inherit these nice properties. So one has a connection between Feynman graphs and correlators, and this is what I want to exploit a bit more in the following. Here I just made the statement, okay, here I actually now look at the correlator with space-time coordinates x, but in principle I can also understand these coordinates x as the region momenta that I discussed previously, so as these dual coordinates. And in that sense, if I relate them to the massless momenta, or to momenta in general, I can understand this either as a correlator with space-time coordinates x, or as a scattering amplitude where these x's are region momenta. Yeah, so I can, in principle, deal with both quantities at the same time. So what are these particular Feynman graphs that correspond to the correlators? As I wrote, these are called fishnet Feynman graphs for obvious reasons. So they are simply constructed by a single 4-point vertex which corresponds to an integration over this coordinate x. And these 4-point vertices are connected by scalar propagators of this form. And it turns out that most of these Feynman graphs, which correspond to Feynman integrals, are actually unsolved, and the solution is not known explicitly. And actually the only well understood example is this simplest fishnet, which is actually a single cross, and the integral takes this form and can be evaluated explicitly. I will show it on later slide.
These are dual coordinates? These are
Here you can understand them as whatever you want. On this slide, they are just coordinates. Now I'm talking about these Feynman graphs. If you want to make connection to this biscalar theory, you can say, okay, either they are space-time coordinates for my correlator, or they can be interpreted as dual coordinates, and I relate them to momenta. Still, I have only a single Feynman graph. So I'm either talking about correlators or amplitudes or individual Feynman graphs. The theory on the previous slide was basically to motivate that these Feynman graphs should inherit nice properties from my original n equals 4 superhang Mills theory.
But when you just use the gamma twist,
Yes?
then your coordinates remain coordinates, right? Or how do they become? How do the coordinates become momenta?
It's just a matter of interpretation. So,
So it's not a transformation that you do at the level of particles or something.
no. It's really just about interpretation. If I would write down a scattering amplitude with these on-shell states here, and I would write down momenta, then I would get the same graph, because the dual graph, or yeah, almost the same graph, the dual graph is also just constructed from 4-point vertices, and I would just interpret these x's now, the difference of x's, to be momenta. It's really just about interpretation. I can also just stick with the idea that these are correlation functions. My point is that these correlation functions should somehow inherit nice properties from this duality, and since they are individual Feynman graphs, I should get nice properties for individual Feynman graphs.
So here's the symmetry that is so that it has conformal symmetry.
Yes, exactly. So these are known to have nice properties like conformal symmetry, and in particular they are UV and IR finite. So I don't have to introduce a regulator to look at loop quantities. I mean, these are all loop quantities as soon as I have an integration. And already in 1980 there has been a connection to integrability given by Zamolodchikov, where he shows that these fishnet Feynman graphs can be used to define statistical vertex models that are integrable in a certain sense. A bit different from what I want to discuss here, and actually he was more interested in the thermodynamic properties, and computed the partition function in the large volume limit. But there was already a connection to integrability.
Sorry, so you said in the loop level there may not be symmetry because of the divergences, right? So here you are making, here the theory you wrote down, there is no UV higher divergence. So tree level symmetry will go over to the loop level symmetry. Is it guaranteed? Just out of here.
It's not guaranteed. Actually, well, this is my question now here. I want to ask what happened to this Yangian of n equals 4 superhang Mills theory, yeah? Well, of course, also this whole limit is very special, right? You take one parameter to 0, one to infinity, you keep a certain product fixed. It's, yeah, of course, things can get lost in this process, and also symmetry can get lost if you project out certain fields.
So suppose I forget about the original Yangian. So based on conformal symmetry, I can construct Yangian symmetry based on this conformal algebra, right?
Yes?
So tree level has that Yangian. And does it guarantee that if I don't have UV or IR divergences, does it automatically guarantee
Tree level, well, the question is already what do you mean by tree level? Tree level means I don't have a single 4-point vertex, right, in my amplitude picture. So, is there chalk somewhere? Here. So if you look at this very simple example, so a single 4-point vertex, then, and these are my coordinates x, and here the external ones, then in momentum space, I also want to make 4-point vertices, I put 2 legs on the corners. So in momentum space I would really have a loop, right? So this is already a one loop diagram. So if as soon as I have one of these 4-point vertices, I already have a a loop quantity. So I can look at three quantities, but these would just be single lines in this picture. Yeah? So
Just numbers. You still have a number.
yes, but number well, 1 over the 6-point amplitude is 1 over p123 squared, or yeah, some. Okay, nothing at the moment. Nothing is guaranteed that I inherit any of the symmetries. The motivation is that I can get these graphs as correlation functions in a certain theory that I get from n equals 4 superhuman theory. And now the question is, can I find these integrable symmetries in the formulation that I had in n equals 4 superhuman theory somehow on these
Sorry,
graphs?
let me ask once more the question that I was asking. Suppose I get a theory where at the tree level I have this there's some symmetry. Okay? It also has at the tree level dual conformal symmetry. Say for example, suppose I have that theory, and suppose I can show without doing any computation, I just show that at the loop level I have no UP or IR divergence. Given these two statements, does it automatically imply that all the loop level answer will also have a conformal and dual conformal invariance?
No, I don't think so. I mean, you would have to, first of all, here, this tree-level Yangian symmetry it's more like an observation, right? It's not proof from the Lagrangian. This is maybe what one hopes to do in the future, but it's certainly not proved. So it's really an observation, and I guess you would have to do the same, make the same observation at loop level, and hopefully at some point find a proof. But I don't think it's clear at all, no. Okay, now coming from this biscalar theory, generating these fishnet graphs, I want to study, I want to understand whether there could still be some Yangian symmetry. And what I want to do is to look at this simplest particular example here, this cross integral, or in momentum space, box integral. And what I can do is to write down a representation of the conformal algebra in my variables x. So these are the generators. Delta is the conformal dimension. And I can act with these generators on the cross integral. And indeed, if one does this carefully, one finds that the generator annihilates the integral if I choose the conformal dimension to be 1, which makes sense since here we are looking at scalars. Yeah? So this is the conformal symmetry I spoke about on the previous slide. And here I actually already called this Yangian level 0 symmetry, but of course not every Lie algebra symmetry extends to a whole Yangian algebra. So at this stage this is still a bit bold, and I should rather check whether I can also find the level 1 symmetry. If you remember, the level 1 generators were simply defined as at these with these bilocal action, and I can write down a particular example, namely the level 1 momentum generator. And if I do this contraction here with the structure constant, I end up with this expression with the Lorentz dilatation and momentum generator densities. And this antisymmetry here is inherited from the antisymmetry of the structure constant.
Is there any classification of level 1 generators? What I mean is that once level 0 generators ready, then all you have to do is to find some solution of paradigms. You get to define complete Yangian algebra. Is there any systematic classification of what are the different kinds of level 1 generators that we can find? This is certainly one of them.
You mean this here?
This is the case, right? You can
This? No, it's not. This is the definition of the Yangian. This is.
So with this definition, it will satisfy the paradigm. If you define level 1 generators,
No. It depends on the representation that you choose for your Lie algebra generators. I mean, here at this stage I just write down an abstract element J, right? But if then I have to specify a Lie algebra representation, and then I have to check the cell relations in principle.
So let's take a semi-simple level 0 generator. Then you define this to be level 1 generator, let's say. Then you have to check that with this definition you are still satisfying the paradigm. I am asking, is there any systematic classification of solutions of paradigms?
Ah.
Once
I don't know. I don't think so.
Most of these Loebbert generators in the literature are this plus some trivial factor like level 0.
Yes, this is.
But is there anything else apart from just this form?
No, this is the definition of the Yangian. I think this will be.
No, but if you take the cell relations to be fundamental, okay, so
Mhm,
this is another
mhm,
question
mhm,
I can ask.
I see.
What are the other solutions that I can write there
Mhm.
so that they satisfy the cell relations? This is certainly one of them, I'm saying.
Mhm,
And there was a paper, an old paper where we found another one, right?
Each of these will modify this.
Yeah, there's a modification of this a little bit. With
At
some
least in
coefficients.
one
and so on.
on S1 you can modify this.
Okay.
So
By whom is this?
Why
paper?
this is the convection matter paper in the context of Harding-Shafter model.
Okay.
Involved some roots of unity and so on and so forth.
Essentially you put one factor of antisymmetric element in the summation. This Ji, this is Jk, Jj and Jk. You put one, let's say omega Jk in between.
Mhm. Maybe you show me afterwards.
But the question is whether there is a systematic.
I don't think people have really studied generically solutions to the Serre relation. Okay, so I evaluate this for the conformal algebra for the special example of the level 1 momentum generator. I get this, which is a differential operator. I act on this cross integral, and I find that the answer is not 0, but given by this relatively simple structure. So I have J labels my external legs from 1 to 4. And now I have this coefficient J times the density of the level 0 momentum generator. Yeah? And what I want to do now is to redefine my level 1 generator in this form. So I add a contribution Vj times Pj. And I define for the cross my Vj to be just minus J, so that I absorb the right-hand side here into the generator, and I find an invariance statement. And well, this is not cheating, because adding this correction here is a well-known thing in the context of the Yangian. This is parameterizes an automorphism of the algebra, and this form here is known as the evaluation representation of the Yangian. So I did not tell you everything when I said that this is the definitely the level 1 coproduct, but you can also add such a contribution here. And now I choose my parameter Vj to be minus J. Actually, in the context of two-dimensional theories, this Vj will play the role of the rapidity if you look at symmetries of the 2D S matrix. But here I have to choose this particular integer values to find invariance of this cross integral. And
So is that comment important? It guarantees cyclicity. If it is not cyclic, was it okay?
Okay, the cyclicity is important because I stripped off this color trace from the scattering amplitude. This color trace was cyclic, so the amplitude is also cyclic. And this has to be compatible with the generator. I will discuss this in a bit more detail in the lectures, so maybe we shift it to there. It's, yeah, just for some experts, maybe this is actually there is not, for 4 points there is not much choice here if you impose cyclicity on the generator. Okay, and now I've checked this level 1 symmetry for a single example for the momentum level 1 generator. Yes. So I can add an overall level 0 generator. So I can add sum over Pj, but this is trivial anyways. But otherwise it's fixed. Yes. So I checked this for a single level 1 generator, and in fact this is sufficient to get the whole Yangian, the whole set of level 1 generators, because by commutation of this level 1 generator P hat with a level 0 algebra I can get the other level 1 generators. So I find that the cross is really invariant under this Yangian of the conformal algebra. So since this is rather abstract and written in terms of these bilocal operators, let's formulate this more in terms of ordinary differential equations. And I told you before that this cross integral is actually known explicitly. due to the conformal symmetry, it's useful to write it in terms of such a function, phi that depends only on these conformal cross ratios, z and z bar, defined in this way. And then these people here have commuted the result, which takes this form here, including these dialogues and logs, which gives the result to the to this cross integral. And now I can sit down and translate my Yangian level 1 invariance statements to statements on this function and two derivatives in terms of my conformal cross ratios, z and z bar. And what I find are these two different differential equations for this conformal function phi here. So this is really what this new Yangian constraints boil down to, namely these differential equations. Of course, here I know already the answer. I know what the cross integral is. It would be much more interesting maybe to have such differential equations on larger fishnet Feynman integrals to which the answer is not known. So a natural question is whether this actually generalizes to larger fishnet graphs. And in order to show this, I need a slightly different formulation of the Yangian, the so-called RTT realization.
Sorry, can you go back one slide? So here, was it x's are which coordinate? Fishnet coordinate. Here you are formulating in terms of what coordinate? Sorry, I got the information. So when you say you are
These are statements about Feynman graphs, and the x's are the external labels of my Feynman graph. That's all you need to know for this.
Okay, so given your Lagrangian, that phi 1 diagram, phi 2 diagram, something. So here, is it Poisson space phi? Are you computing?
Yeah, then this would be my space-time coordinates. Yes.
I see.
But I could also interpret this as a scattering amplitude via this dual picture as a box.
And the fact that your Yangian invariance is, you get a non-trivial PDE because you have not directly shown that there is a dual conformal invariance, or you have not tried to write things in a nice way. Otherwise, it would have been
Right. By introducing z and z bar, we solve the conformal symmetry, but not the dual conformal symmetry or the Yangian symmetry. Yes. Right. Exactly. And yeah, I think an important thing is that this Yangian symmetry now formulates both of the symmetries in the same variable. So I can write down these additional constraints on the same function where the conformal symmetry is already solved. Yeah.
I guess what has to be the same that instead of thinking about this cross, now if you look at box, and you show the box is also conformally symmetric, then we have shown both
Yes.
conformal and disconformal, right?
Yes. Yes, I could also do this, but say I want to study larger fishnet graphs. I guess I would like to formulate my constraints in one set of variables, right? And this is where you have to go to the Yangian language, I think. Okay, to show this for larger fishnet graphs, I use a slightly different formulation of the Yangian. I collect these Yangian generators in terms of a generating function, this monodromy T of u. U is the spectral parameter. I will also comment a bit more on this in these lectures. And then the Yangian relations are encoded in these so-called RTT relations. So this is something like a generalized commutator for this monodromy here with a, well, generalized structure constant given by this R matrix. And in this particular case of the R matrix, of the Yangian, this R matrix is just the identity plus u times the permutation operator, and this permutation operator just flips two spaces. So spaces here means basically the external legs of my amplitude.
So if I expand this into U and V, what do I see this relation? I first see the fact that the J's form an algebra. I just want to understand this RTT relation in the expansion and get familiar with it.
Yeah, you would have to expand T in terms of the generators.
So you will see the fact that the J's form an algebra, then J hat forms a representation of that algebra, and then J hat gives you
Yeah.
J double hat and so on.
Yes, right. The higher terms will all be generated by iterative commutation of the lower level 0 and level 1 generators. So I can explicitly solve this relation for this particular case in terms of
Is there a way to express that relation in this replicating language? In the language?
I'm not sure how you explicitly map the serial relations. They are included in this language. I mean, yeah. Generically, you also need an additional quantum determinant constraint equation if you don't look at GLN. Some more comments on this again in the lecture. To map, how to see where explicitly the serial relations map to in this is not clear to me. Well, the mathematical statement is that the solution to these equations in terms of the generators J and J hat can be mapped to the solutions of the first realization that I gave you on the previous slides. But, yeah.
Sorry, what does this one mean which is there? Or what does it T1, T2?
This relates just to abstract spaces. Like, for example, my space of the external legs. Yeah, so spaces I act upon.
1 and 2 meaning external leg 1, external leg 2, or is that what?
Well, in this case, the 1 and 2. So the monodromy. The monodromy is this product of Lax operators. Yeah, these Lax operators can also be. Well, this has nothing to do with this. Lax operators can also be written as a cross. Yeah, you have a physical space they act on. This would be my external leg. And I have an auxiliary space. Yeah, so the Lax operator is generally written like something of this form. 1 plus u is the spectral parameter, and then you have some physical generator and some auxiliary generator. Yeah, so this acts on this space, and this acts on your physical space. Yeah. And the monodromy is now the product of these Lax operators in the auxiliary space. Yeah. So I multiply these Lax operators with each other. This is this product here. And now I have these are my physical spaces. This I did not write explicitly as indices of the monodromy. They would act. The monodromy acts on the whole chain of external legs. Yeah. And I have this one auxiliary space, and this is what this 1 and 2 refers to. So I have a monodromy acting on 1 and 2, and yeah, 2 abstract spaces that are intertwined by this R matrix. Okay, so I can explicitly solve this for the case of the conformal algebra with these Lax operators, which depend on 2 parameters, delta plus and delta minus, and these are essentially just related to the spectral parameter and the conformal dimension of my external leg. So it's just a reparameterization, which is a bit more symmetric. And, well, one can also write down explicitly the solution here for these Lax operators. People have done this in this paper, but I won't do this here. Just to illustrate things better, I introduced this pictorial language that each Lax operator corresponds to an arrow, and the product of 2 Lax operators is indicated by this connection line here. Yeah, so the question now is, what does Yangian invariance mean in this language? And if you think that the monodromy is just the expansion in terms of these generators, and all these higher orders here should annihilate my Yangian invariant, then all that remains is my identity. So the invariant statement of a Yangian invariant IN turns into such an eigenvalue statement under the monodromy. So acting with the monodromy on the invariant has to be an eigenvalue times the invariant itself, and this is then the same statement as my Yangian invariance, my invariance under these higher orders here. And in terms of pictures, it's just this. I take my graph, I put a monodromy once around, every arrow is a Lux matrix, and invariance would now mean that I can somehow pull my monodromy through this graph so that I only end up with an overall eigenvalue function times the original integral. So how can one prove this? The idea is really to use some relations to pull this monodromy through the graph. And the most important relation in this process is this so-called intertwining relation for the scalar propagator 1 over x12 square.
So why allowing an eigenvalue? Why not just taking it? Why not just saying that the invariance should just mean that E should annihilate that?
Because I have this identity here in the expansion, which does not annihilate the. Yes. So to prove this, I have to pull the monodromy through the graph. The most important relation is this one here. Here I have a scalar propagator, and I act with two Lux operators on it. Yeah, L1 and L2 act now on these two coordinates, 1 and 2. So these are. Here are the differential operators of my conformal algebra, these j's here, so they act on coordinate 1 and 2. x1, 2 was just the difference of x1 and x2. And the idea is now that I can pull this propagator through my Lux operator, through my product of Lux operators. And this is true if I have a certain combination of these arguments here. So the bullet and the star can be the same on both sides of the equation. The important thing is that the parameter here, the second parameter of this Lux and the first parameter of this one have the difference 1. And then one can show that this relation indeed holds. And in terms of pictures, it simply means that my propagator, which is this solid line here, acted upon with this product of two Lux operators with these particular arguments, can be disentangled from this loop of Lux operators.
Disentangling, how is the delta label changed? I thought delta is kind of a sequential label, right? Delta.
You mean as external variables, or?
Can you go to the previous slide? I thought there was no slide. Yeah, so here, what are the difference in labels?
I will tell you on the next slide. Yeah. So I will tell you what the delta is in this process. So when I pull this monodromy through the graph, the arguments of the Lux operators will change due to these relations. Yeah.
So the goal is to show that this P operator acts nicely on arbitrary distinct graph. Is it so?
Yes. This Yangian invariance means that it acts nicely, and nicely means that it's an eigenvalue equation. Yes. Exactly. Well, as I said, this is just the most important relation. I can use other relations here, but yeah, things become very technical. So I did not. This one? Yeah, I guess in this particular picture, at the moment, at this stage, I cannot use this relation. Yes, that's true.
What we need here is probably this thing crossing the vertex.
Yes, but yeah. Well, okay. The idea, since I also wanted to include this gravity part, I thought, okay, I don't tell everything in all explicitness. So the idea is, for example, if you have the cross integral, yeah, and you put a monodromy around, like this, yeah, then you can introduce, you have an additional relation where you can introduce an identity. How was it? Like this. Yeah. So this will essentially just boil down to introducing a 1. Yeah? This is another relation one can use. And by introducing this, so if this is actually the same graph here, then now I can pull this loop here. You see this is now exactly what I've drawn here. If I draw it like this, I can pull it through, and again here and here and here. So this is how this mechanism works. I need additional relations. It's just that this is the most important. It's the most important because it's also needed to prove, for example, that this is the identity, and it's important because it has the form of this Yang-Baxter equation, right? It's a intertwining relation for this propagator. Okay, so this is just to give an idea of the mechanism. I use such relations to pull the monodromy through the graph, and then I can really disentangle the monodromy from the complete graph and pick up in this process some prefactors which give me the eigenvalue function for my eigenvalue problem. Now I should tell you what these deltas are, as was noticed before, and I do this on a particular example. So I have my graph, I put the monodromy around, and now I have the freedom to choose my parameters. So first of all, I have chosen an origin of my monodromy, right? I could also could have put it at a different point. This doesn't matter. The construction has this freedom, and then I can choose my parameters to be 1, 2 here. I can shift all parameters by an overall constant. This also doesn't change anything. And then the simple rule is that I stick with these parameters 1, 2 if I'm on the same line. If I turn right, I add 1. Turn left, subtract 1. Turn right, add 1. Turn right, add 1, and so on. So that in the end, I have just 1, 2 on the top, 2, 3 on the right, 3, 4 on the bottom, and 4, 5 on the left. Yeah?
Last time when you defined delta k plus minus, you had related to the conformal division.
Yes?
Now you're just putting random numbers.
Now?
Now you're just putting numbers that you see there.
Yes, but the numbers that I've chosen are such that the conformal dimension is 1 on each leg in this picture, yes. So I have scalar particles. The conformal dimension has to be 1 here.
Wasn't your rule that delta k plus was a conformal division by 4 and delta k minus was conformal division by 4 plus 4?
Well, let's go back.
Are we to define delta k plus and delta k minus in terms of conformal division of that way? Why do you have a third one? I thought all these are just conformal division.
Well, if you solve this relation, these two parameters give you two equations. Delta plus equals the first, delta minus equals the second entry. You can solve this for delta, and you will find exactly that you get with these parameters I've chosen, delta equal 1 on each of the external legs.
This equation at the bottom is not a definition of delta plus and delta minus. You wrote u plus delta plus and then u plus delta minus 4 over capital delta minus 4 over. So does it mean that delta plus is capital delta minus 4 over or not?
I guess maybe I should. Okay, sorry. I think I should have called these parameters here not delta plus and delta minus. These are my delta plus and delta minus. Yes. Sorry.
You kind of offset.
Yes.
So the rule is delta plus and delta minus is not equal to minus 2. So delta plus minus what combination of delta plus and delta minus is a conformal division and what combination is a number?
The result should be one.
No. But as you say, we took from here that the addition is minus 2.
No. The difference between delta plus and delta minus should be delta minus 2.
Right.
Which is minus
Right.
1.
Yes.
This is what all these
Yes.
things are 2, 1, 3, 2, 4, 5.
Exactly. Yes, right. Here I should use different labels.
So
Yes.
we can ignore that part.
Okay. Yes.
Okay.
Yes.
So clearly now you want delta plus the delta minus plus 1. Okay. From your theoretical data theory.
I want delta plus minus delta minus plus 2 equal delta, I guess. I guess this delta plus minus delta minus plus 2 equal delta.
And you have the delta is 1.
Yes. Okay, and this is the choice of parameters that makes that compatible with these rules to pull the monodromy through the graph. Okay, you can ask, why do I have 2 parameters? In this picture it looks I only need 1 because the difference is always only 1. But if you use these rules, the difference between the 2 parameters and the Lax operators will not remain always 1. So you really need 2 parameters in this problem. Okay, so this is the idea how to prove the Yangian invariance of these particular fishnet graphs. The question is there only this particular class, or can I generalize this further? And one thing would be to go to different dimensions. So I now look at the propagator in d dimensions, which comes with the power 2 minus d. So I would need a generalized intertwining relation of this form, and I wrote this particular form because here we find solutions for the Lax operators in 3 and 6 dimensions that obey this relation for the d-dimensional propagator, and using this relation one can actually generalize this also to 3 and 6 dimensional graphs, which now have a different structure due to the different power of the propagator here. So in 3D I have this triangular graph, and in 6D I have such a hexagonal graph, and from each of these graphs I can cut out along a single contour a piece of the graph which then corresponds to a Feynman integral, and which via this mechanism can be shown to be Yangian invariant. Sorry?
What is not being d-dimension and 5 equals 5?
Well, it's not clear how to do this. What you would need is a solution for these Lax operators here, right?
So you don't know L.
Right. And yeah, I mean these dimensions are also not so unnatural actually from the. There's it's not known. Well, yeah, the point is this here, as I've shown you, can be obtained from this biscalar limit of n equals 4 super Mills theory, of gamma deformed n equals 4 super Mills theory. This one can be obtained from a biscalar limit of, not biscalar, but a double scaling limit of gamma deformed ABGM theory, but it's not known how to obtain this 6-dimensional theory. That would be very interesting, whether there's a mother theory that generates these graphs.
Just remind me, this limit was taken for the large n, right?
I'm looking at large n, yes, at planar graphs only. So it's also not unnatural to look at these particular classes of graphs because they were already discussed in this paper by Zamolodchikov. He did not only discuss these fishnet graphs, but he also said that these 3 and 6 dimensional examples also lead to integrable vertex models, but integrable in a very different sense, at least superficially, not in this language of the Yangian as in n equals 4 super Mills theory. Yes.
So, but knowing the LZ functions is the same as the integral?
No, not necessarily. Still, you have to prove that you have that you can disentangle the monodromy from these graphs. I just wanted to say this is the bottleneck for other graphs. That, yeah.
So you're saying that these are all graphs have the property that you can take that line around it and then collapse.
Yes.
And
Up to this stage. Well, these are all the graphs including scalar propagators. Yes.
so
Yeah.
so the T equals pi is a rectangular graph.
You could- okay.
Is it true that for T equals pi, if I tried to do this, it would not be true, that I would not be able to collapse the line around it into
Well, first I would need an LO. Suppose you know the answer, you say, then I don't know. I haven't tried this in D equals 5.
I thought you only needed relations of the sort of what is the last step.
This is the generalization of this relation that I called most important relation. Yeah. So
I think the other relations you don't. There are other relations.
there are other relations, and you can also write down the generalizations. Just for this talk,
Yeah, sure.
I didn't.
So you can generalize all the relations you need.
For these graphs, yes.
Yeah.
Yes.
So pi dimensions as well. The particular graph as well.
So what is the center of the graph?
The one is not drawing.
Can you draw it? I don't think it can be drawn.
We not time the plane with it. So it's the graph. You don't need to
This is
understand.
not from general graph, this is from regular triangle of the plane.
Why is regular timing done? What is that period there? I thought it was
Line
just like.
graphs are not using the regular triangle.
It is calculating finally a correlation. It is connected with regular triangle.
Like, but the hexagons, whatever you, the way you want it, I don't think you will get it. It has the same variance, but number of legs on the other, but it will be the same maximum. That will tell us that it will be a regular line.
We cannot use the correlation. Oh, I just do not connect. Oh, okay. Then it makes sense.
Well, I'm finding that we can apply this to the regular tilings of the plane. I don't say that it has to be a regular tiling to, I don't know, at least I don't have a proof that Yangian symmetry implies that you have a regular tiling of the plane, yeah?
No, but I'm not saying it. So if it were to be thought of as something coming from Feynman diagrams, then the balance in vertex should have the same balance. If the theory has one vertex.
Yes, right, if the theory has one vertex. And the question is, perhaps one can even generalize this. And in order to do this, I go back at this original motivation, namely taking this biscalar limit from the deformed n equals 4 super Schmidt theory. Yes?
Can I make this game of contracting the monodromy line for a square graph in T equals 3?
No, I don't think so.
Very few studies have done this, but it's
I guess you already don't have conformal symmetry.
okay.
So, yeah.
Okay.
So if I go back to this gamma deformed theory where I actually had 3 parameters and now I had used only 1, I can take different limits. So I can take different combinations of my limits, and one that I can take is this particular limit where I keep 2 coupling constants, psi. These were the products of the Toff coupling and e to the gamma. And I actually end up with a model with 2 fermions and 3 scalars. Yeah? So I have more vertices. And also here it turns out that one can write down the respective graphs, for example, with these Yukawa vertices, and generalize this notion of Lux operator monodromy construction and show again Yangian symmetry of these graphs. Well, what you need are different representations of the conformal group, non-scalar representations, but things become a bit more complicated, but in principle the mechanism is the same, and by this mechanism one ends up with these new types of graphs that, for example, in the paper by Zamolodchikov were not studied, probably because you only looked at scalar graphs. But also these have Yangian symmetry now. Yeah. Yes. Yes, you can also mix. Yeah.
So another point I want to mention is that because of this particular limit, the gluons are decoupled. So the gauge symmetry is not a gauge symmetry anymore. It's just the global symmetry of the theory. So that's why you can think of this thing that you're computing as a correlation.
Exactly.
Otherwise, this would not be gauge symmetry.
Yes.
So there is no way I can
Exactly.
generalize it to a gauge theory.
At least in no obvious way. Exactly. This is the point why we haven't looked at these correlators before in any principle. Yeah. Right. Okay, so this is the end of the first part of the talk that I sketched, and the question that I want to ask now is whether such structures, Yangian symmetry, conformal symmetry, so here it seems really important to have conformal symmetry as an underlying structure, right? So everything is built on conformal symmetry.
So another question. So the models that you have discovered, they are all non-uniform, are they?
Yes. And well, I want to ask the question in general whether conformal symmetry could also survive in a theory including gravity. And of course, the most interesting theory would be Einstein gravity, because it's the most basic. Yes.
Sorry, it can go. With Zamolodchikov source, you said Zamolodchikov analyzed three kinds of graphs.
Yes.
Oh, sorry. Can you make the statement once more? What was his point? That these kind of graphs could be integrable.
He said that these types of graphs can be used to define vertex models. Well, obviously they have vertices. And that these vertex models are integrable. And what he used was some kind of star triangle relation to argue for this integrability. But yeah.
So it's not. So till now you have just seen any single force triangles gives this or any single gives this. But it's not guaranteed that only one model will. There can be a lot of models which can give rise to this kind of graph, right? If it has to be practical.
Possibly, I don't know. Yeah.
Is there any understanding of this fishnet graph from your side?
No. I think this is really a big open question.
So Zamolodchikov's models were, so these were vertex models given by positive Boltzmann weights and so on. But I'm saying that, these seem to be generated by some non-unitary duality.
As Feynman graphs, yes.
Feynman graph. Which would mean that these would correspond to complex Boltzmann weights or what? I mean, if I'm trying to interpret these Feynman diagrams as as a sort of particular on a lattice, or partially something on a lattice and so on. So what would that correspond to? That for this particular lattice configuration, I have a complex Boltzmann weight. Or how does this map? Does this thing map to the vertex model? Is it
I would have to remind myself.
so I know how this game goes for the matrix model. For the matrix model, these correspond to basically Boltzmann weights of basic field theory, and that having interpretation in terms of static weights and so that is some good interpretation. And so
I don't remember what the exact definition of Boltzmann weights was in this
there
one.
is no value to sorry. There's no sum over lattice. So yeah, so I don't quite understand how Feynman diagrams are mapped from that to I mean, what I mean to say is that suppose I have a vertex model, some static system, and for that I have some specific lattice. What is it? Some fixed gradient lattice. And so for different spins or whatever the variables are, I have different Boltzmann weights, and I keep summing over all kinds of Boltzmann weights. But okay, how does it work? Different Feynman diagrams would mean that the lattices themselves are.
No, I think
No, you have only one lattice there.
single Feynman diagram showing it to be
Exactly.
Yangian invariant and take a different. That's the statement about integrability on all sorts of lattices.
So in Zamolodchikov's
I see.
picture, he has just one lattice of each type, and this lattice is his vertex model.
So that lattice is vertex. Okay, so on the other hand, if you started from this, what is it called, the biscalar field theory,
Mm-hmm.
that would generate all these. Okay, fine, I understand. Now here, so does it mean that Zamolodchikov had complex correspondence weights or not? That's what I'm saying. You know, it should correspond to some over e to the power minus.
Mm. I don't remember what the definition of the Boltzmann weights was. I don't know. I can show you afterwards. But, yes, yes, yes. Yes, exactly.
And the summing over the various energies is like integrating over the x's corresponding.
Yes.
Yeah.
Is that manual interpretation wrong?
So for each of these vertices, okay, so like in the middle one, there should be the quatic coupling constant.
Right. That
That
is
comes
normal
in
one.
Yeah.
That is normal
He has no
one.
coupling
And
constant.
then the propagator. So you're saying it need not have complex.
Anyway, symmetry can be mapped to this model.
I see. I see. Okay, all right.
But for each Feynman graph generates a finite part of the line.
Right, right. And yeah,
Correspond to given formulation, which you see.
yeah. Actually, what he computed was only the infinite lattice partition function. Yeah. Right, compute. Yeah. I don't think. I'm not even sure he gave the proof. It's a very short paper. Yeah. Okay, more questions on this? If not, then I come to this gravity part and to the question whether one can think of amplitudes in gravity, whether one can introduce some notion of conformal symmetry here. And if I naively think about this and I look at the Einstein Hilbert action, then the coupling constant has a dimension. If I go away from 2 dimensions, so naively I should not have a conformal symmetry. And in that sense, I would say, okay, if I have a conformal symmetry on amplitudes, it must be hidden in some way. Yeah? It's not that I would go to the action, write down my conformal transformations, and translate them to the amplitudes as I did for Yang-Mills or n equals for super Yang-Mills. Yeah? And the idea here is to look, well, of course you would not, probably not look at this question if you would not have some indication for it. You would not get the idea to show now that gravity is conformal if you don't, Einstein gravity is conformal if you don't have any hints for this. And the hints that I want to discuss here come from string theory, even though eventually I will be only interested in field theory scattering amplitudes, so in graviton scattering in Einstein field theory, and well, the relation is just given by taking the inverse string tangent alpha prime to 0, so that I can also deduce statements about field theory scattering. So this slide is just to motivate that I'm really interested in the field theory scattering and not in any string scattering. So what I want to look at is a particular soft limit in string theory that these soft limits has been discussed by these people here in the last years in various papers. And I want to look at the soft limit of an amplitude with n gravitons and 1 dilaton. And the dilaton carries momentum q. And I want to look at the soft limit in this momentum q. And what people have found then is this expression here. It's not so important that you try to understand this in much detail. The important thing is the structure, namely, firstly, that I have here these operators as delta and as delta prime, which include the conformal generators with conformal dimension delta being 0. So these are differential operators that enter here in this soft limit. And secondly, an important thing is that if I take the field theory limit alpha prime to 0, then tree level amplitudes with n gravitons and an odd number of dilatons actually vanish. Yeah. So if I apply this knowledge to this equation of the soft limit that these people have found here, then I see here I have an amplitude with 1 dilaton, and here I have an amplitude with n-1 gravitons and 1 dilaton. So actually this and this should vanish in the field theory limit, yeah? Which means that only this first line here remains, which is this blue equation. Yeah, and you see, since S delta and S delta prime include the conformal generators, and I have a 0 on the left-hand side, and this relation should hold at for arbitrary q. If this were here the field theory graviton amplitude, this should predict conformal symmetry, which is something we would not expect from the action as argued on the previous slide. However, there's a small caveat that this M twiddle, yes?
Does this particular combination mutually be differential? Or is it just
Well, since I expand this here in Q, and it should hold for arbitrary Q in principle, this should also predict invariance under dilatation operator and special conformal generator separately, if this were the amplitude.
So why do you say it should hold for arbitrary Q? I thought this is a statement about expansion in Q.
Yes, okay, it's a okay, what I do in principle is I rescale Q by epsilon times Q, and then I expand in epsilon, right? But then I get an expansion in Q, but still Q can be varied. What is this? I discuss on the next slide. In principle, this M here was the scattering amplitude, and here I've written down an M twiddle.
Curly M in the second line, is that a curly M? Like
No, the curly M is just the M with the delta function. Okay, I will tell you explicitly what M twiddle is here. So I have this statement, this blue equation for the M twiddle, and this M twiddle is in principle this integral here, which is my string, turns into my string amplitude when multiplied by this overall momentum delta function. Yeah. So this here would really be the amplitude, and it's the field theory amplitude if I take alpha prime to 0. Yeah. However, my M twiddle alone without the delta function is not yet the scattering amplitude, and will not be the field theory scattering amplitude in the small alpha prime limit. It's the limit of this particular integral. Yeah. So if I look again at my blue equation, and now I have spelled out these operators as delta and as delta prime in terms of the conformal generators, then here you see that the delta function does not multiply my M twiddle, but there are these operators in between. So in order to turn M twiddle into the amplitude, I would like to bring the delta function next to this integral. So we can do this at leading order in Q. If I pull D through the delta function, I pick up some factors that I can actually include into the scaling dimension. The dilatation operator has simply this form. Yeah, here I have the scaling dimension, and I can, if I set the scaling dimension to D minus 2 over n, this is now in D dimensions, then I can pull D through and write this first line here as this equation. Yeah? And now I have really delta P times M twiddle, which then really turns into the M twiddle, which turns into M, which is just the field theory amplitude. So at leading order, what I find is this statement that the dilatation operator with this particular choice of scaling dimension annihilates my graviton field theory amplitude. This is nothing very spectacular because, well, this really just measures the scaling. So this is a well-known fact about these amplitudes, that they scale in this way. It's more interesting if I go to the next order, where I have the special conformal generator. And again here I want to bring pull the special conformal generator, commute it through the delta function, so that the delta function is next to my M twiddle. And I can do this, and I get a part that actually looks very nice. So I get K with, again, this particular value of the scaling dimension on the field theory amplitude. And this would be 0 if there were not this nasty red term. You see that this red term vanishes in 2 dimensions, but yeah, we are interested in 4 dimensions or in higher dimensions. And here I have again this m twiddle, so I have this red term which spoils my conformal symmetry argument. And you see that this conformal symmetry would be much less trivial because the special conformal generator is a much less trivial second order differential operator. Well, I can pull it through, but then I will generate additional terms. So if I want to write something down, k on something plus a leftover, then yeah, this is.
Those terms could also be expressed in terms of conformal generators, perhaps?
No, I don't think so. And what you will get is also derivatives of delta functions, right? So the question is, can I somehow still find an argument about conformal symmetry, and in particular special conformal symmetry, in the context of these three-level graviton amplitudes? Because it's already interesting that the generators enter in this soft limit here. So what one could think of is just to take the field theory tree-level amplitudes and to act with the special conformal generators. The expressions for the amplitudes are known, and I know what the differential operator is, so I could simply act on the amplitudes. A problem here is that this second-order differential operator does not commute with my on-shell constraints. So the momenta should obey these constraints here. K square should be 0 since I have massless particles, and K should also contract with the polarization vector to 0.
You're doing this now for gravity, right?
And I'm looking at d dimensions. That's why I cannot really not simply go to my lambda bar spinors, which would solve these on-shell constraints. Yeah. So the problem is that K does not commute with these, and so it does not really map amplitudes to amplitudes or really induce Ward identities on my on-shell space, and rather takes me off this space, which is yeah, not really something I want. But the same question actually holds in Yang-Mills theory, right? I have the same momenta, the same polarization vectors, and also there the special conformal generator does take me off shell, even though I know that there I should have conformal symmetry at least in 4 dimensions. Yeah, so what I can do is to act explicitly with the special conformal generator on the Yang-Mills amplitude. I get this structure, which is basically dictated by Poincaré symmetry. And even for delta equal 1, which corresponds to 4 dimensions, the 4-dimensional scaling dimension, I find a non-zero expression. So I don't find the conformal symmetry that I would expect. One thing one can remember here is that that these amplitudes should have a cyclic symmetry and also a reversal symmetry, because I stripped off this color trace. Yeah, they inherit this symmetry from the color trace. However, this cyclic and reversal symmetry is only obeyed modulo these on-shell constraints, of which I've shown you on the previous slide that K does not commute with them. Yeah, so these symmetries don't hold. So K does not preserve this space on which the symmetries hold. And one guess could be that it helps to make these symmetries manifest. So to really define an object Cn of an where I simply sum over all the permutations manually, so that I don't have to use on-shell constraints anymore to see that the amplitudes have this symmetry. And on-shell, since these are all symmetries, on-shell I have that this object is actually the same as my original expression for the amplitude. So on-shell, this is not an interesting thing. What's interesting is that now, indeed, I find that the special conformal generator annihilates this symmetrized object for scaling dimension delta equal 1. So in this empirical way, I find that my conformal symmetry is restored by by making these permutation symmetries manifest.
But if you talked in the beginning, first few slides, when you talked about scaling amplitudes to have a conformal symmetry, is this what you meant? That you need to symmetrize between the scaling and the
No. At that stage, I formulated things in 4 dimensions, so I used these on-shell spinners, lambda bar, which solved the on-shell constraints. So I did not have this problem.
And K respected that symmetry.
K respects this constraint
So
then.
what happened now?
Now I'm looking at d dimensions. So I cannot introduce lambda and lambda bar in d dimensions. I want to look at general dimensions because this soft theorem was independent of.
Sure, but in 4 dimensions there wouldn't be any problem.
In 4 dimensions, if I use k and epsilon, there would be still a problem.
Why?
Be-
How is the problem dependent on your choice of?
Because I have not resolved these constraints. Because my generator takes me off the constraint hypersurface.
When you solve them also, then you should have seen this problem in some way. I don't understand. I mean, you're saying that if you solve the constraint,
Yes.
then the action.
If I have variables that manifestly respect the constraints, that manifestly solve the constraints, and my k then in lambda and lambda bar k would commute with this.
Doesn't that mean that
I'm just
that
using.
k should respect constraint? Because once you solve them, then you are saying that k does act nicely in this case. I mean, if this were true, then you shouldn't even expect k to be a differential operator in the lambda lambda bar space.
But the point is that in the lambda lambda bar space, the differential operator only acts in the direction of the onshore hypersurface.
Why don't you just you take a new k and you take that k to be the projection of that k, projection of this k onto that flux.
How do I do this?
But is that at least conceptually correct? Then that is
Okay, you mean this is?
lambda lambda bar k, right?
I guess conceptually, yes. And in some sense, the symmetrization is something like this, yeah.
So, yeah. So here, okay, just to make sure. So, sorry, I might have missed. So earlier you had amplitude where you applied k and you got something non-zero value, right? So vi times something.
That was Yangian symmetry, yes.
That was Yangian symmetry. So
This is not related to this.
that's not related to this. So I'm just trying to understand. So earlier k acting on an was it zero or not zero?
There it was 0, yes. Because I had these variables lambda lambda bar that solved the onshore constraints, and I was in 4 dimensions.
And the point was here, how is it, so when you make it cyclic, it becomes zero. You're saying when I make it cyclic, it becomes zero. And in the lambda lambda bar variable, is it that it becomes automatically cyclic, and in this variable it is not cyclic? Is that the point, or?
No, it does not become automatically cyclic. In the lambda lambda, okay, in the lambda lambda bar variables, this will not be a problem.
Yeah.
But it is a problem in these variables, and this is now, at least heuristically, a different way of dealing with these problems. Because I know that the amplitude has these symmetries only modulo the onshore constraints. So if I make them manifest, I don't have to use onshore constraints anymore to see these symmetries. So I define a better objects for the conformal generator because
I mean, by
It's-
amplitude, one does mean that the external space are on-shared, right? So the amplitude does have this.
the amplitude has, yes, exactly, that's the statement here. So the symmetrized thing is exactly on-shell the same as the unsymmetrized thing. Yeah. Okay, now I want to do exactly the same for the gravity case. I take k, act on the graviton amplitude. Again, I don't find a 0 result, not even for delta equals 0, which would correspond to 2 dimensions, where I've seen that one might expect nicer things. However, again, here I have the statement that I have a permutation symmetry. In this case, it's full permutation symmetry, Bose symmetry, that's obeyed only modulo on-shell constraints. And I make this symmetry manifest. So I sum over all permutations of the external x. Again, on-shell, both are the same. But now, also here, I find that k annihilates this symmetrized expression. And interesting, this works not only for a particular value of delta, but it works for any value of delta. Which is, yeah, surprising probably. Because this is not something we would have thought from this soft theorems. Okay, let's.
So how does this work for it? I mean, I thought this delta is essentially telling you that if the external legs transform as if they have conformal dimension delta, then that's what happens.
Yes, right.
What does this mean that it works for any length with delta?
I don't know what it means. It's an observation. Still, this is a non-trivial second-order differential operator. Okay, let me make this a bit more precise. Exactly. This is the expression for the special conformal generator. So it means that the single derivative annihilates the symmetrized expression. Exactly.
So
But this is very much in agreement with the soft theorem statement, which was this thing where I had the red term that spoiled my conformal symmetry, because here I have a single derivative as well. So it's, I don't know, it gives at least a consistent picture that this vanishes, because then also this additional piece here vanishes. Still, things work for general delta.
But for dilatation, you need delta to be that, right?
Actually, I also, okay, this here, it was on the delta stripped amplitude, yeah? What I want to do is to act on the full distribution, so I want to pull k also through the overall momentum delta function. And if I do that, I actually need also delta to be d minus 2 over n. I get this additional factor by pulling it through the delta function. So I find that on these symmetrized graviton amplitudes, I really have special conformal and dilatation symmetry. Moreover, translation symmetry and Lorentz symmetry are trivial, so I really have the full conformal algebra that annihilates this symmetrized tree-level graviton amplitudes. Well, at this stage, it's an observation. It's not so, it's not clear what it means, but at least for us, it was an unexpected thing, and we only became interested in this due to these soft theorems, which seem to predict some role of the conformal generators. So let me summarize.
Sorry, just one.
Yes.
So here, there are two statements. In general dimension, I don't have k in terms of lambda lambda, so onselfness is a bit of a problem.
Mm-hmm.
I understand. But the second thing you're saying, if I make it symmetric, then it becomes automatically, you can solve by making it symmetric.
Making it symmetric gives me this invariance, yes.
Yeah, so are these two related or these two are unrelated?
I would say it's not clear. This that we can use the symmetrization to make to establish the conformal symmetry is a heuristic observation. So we find that symmetrization, which has a problem with onshore constraints, can resolve this. Why this is the case, we don't have a proof for this.
Is it possible to, for a situation, say I'm in a dimension where I can write down momenta in terms of some lambda, but I don't have this conformal symmetry or this symmetry, k symmetry, but by making cyclic symmetry, it becomes a conformal. Is that a possibility?
I think it's a possibility, yes. Okay, so in this talk, I've tried to give two ideas of hidden symmetries in these scattering amplitudes or Feynman graphs. I have first discussed these fishnet graphs that inherit some integrability properties, Yangian symmetry from n equals 4 Mills theory. Just two particularly interesting points for the future would be to now really try to use this integrability where you have many tools to compute Feynman graphs, because most of these are not known explicitly, these integrals. The second question was also already asked, is there some ADS dual of these fishnet theories that's also not known? Because here you take usually the soft coupling limit, weak coupling limit, sorry. And in the second part, I discussed briefly this graviton scattering, where curiously we also find a conformal symmetry. It has some very special features like this scaling dimension that depends on the number of particles and the dimension. But still, the amplitudes seem to be invariant under a representation of the conformal algebra. And it would be interesting to clarify whether this is just a coincidence that happens at tree level, or whether one can find a proof for this, maybe even from the Einstein-Hilbert action. And this is still completely open, what's behind this observation. So, yeah, thanks.
Any questions?
Yes?
symmetry. Here you saw something. Are you going to connect or are these two disconnected?
It's not disconnect. I mean, these fishnet graphs also have dual conformal symmetry. So you can, in our paper, we relate this Yangian symmetry to the dual conformal symmetry also.
Yeah, but does it help to compute for me integrable falsifying these amplitudes?
Or what I mean,
It
suppose
doesn't-
I ask from here, what do I get back in the original theory?
Okay, I guess. Well, one thing you could learn would be really, as I write here, to compute integrals using integrability. Yeah. For example, this double box integral, two crosses. It's an amplitude that also appears in n equals 4 supering Mills theory. So an integral and an amplitude actually at two loops, it's the only contribution to a particular scalar amplitude. So if this could help to understand this integral better, it would also help to learn something about n equals 4 supering Mills theory. I think an interesting thing is that you here really break it down to Feynman integrals, which enter in more context than just n equals 4 supering Mills theory. So you really learn something that's independent of ADS-CFT. And in the other direction, I think it might be very interesting to understand what do you actually need to have an integrable four-dimensional quantum field theory. So in this direction that you take limits where you have more particles like these scalars, can you somehow reconstruct n equals 4 somehow and see what are the ingredients that you need to have integrability. And of course for that it would be very important to understand whether there's also an ADS dual of this theory.
You made a comment when you talked about conformal symmetry of graviton
Yes.
that one does expect these amplitudes to be rotation invariant if you take then if you take the delta to be d minus 2 over n.
Yes.
How do I see that? This is the dimension that I.
Well, basically it just means how the amplitude scale, with which power the momenta enter into the amplitude, right? And I don't know how to prove this formally, but well, you know the explicit expressions for the amplitudes, so you can already see this. I mean, scaling is not so.
So you are saying the.
We have the d-dimensional expression for the amplitude.
What if it would not understand is if the fact that there is the n in the denominator, where n is the number of external legs. So the overall delta is just a constant, no matter what n is.
Okay. What? What?
The sum overall delta. The overall scaling with the center of mass momentum is constant. That's the thing that I see. Why is it constant? Maybe it's
Okay. Well, okay. You have this is a scaling dimension for each external leg, right?
yeah.
And you have to sum over n of them. So you will get n times d minus 2 over n. So the n, yeah.
Yeah,
But
why do I expect that to be the case?
Well, I'm not sure how to prove this from first principles. Yeah. If you look at the amplitude,
Do you
see.
expect any dual conformal symmetry?
I do.
Checkable, right? At least with 3 levels.
Sure, but
Some amplitudes and you symmetrize them and see whether.
I mean at this stage the conformal symmetry.
Perhaps not those, but you Yangian.
No, I guess I would not expect this. At least not in Einstein gravity. That's too much, I guess.
Next question.
But maybe one can define some Feynman diagrams, including gravitons, which have similar structures. That could be possible. I don't know. Then you have to think again about divergences,
No,
but
but this is at tree level only, and structure only at
tree level.
because that's what you're saying.
Yes, sure, right. Mm.
Well, the status of conformal symmetry is probably not clear at this level.
I don't know, and I also don't know in which sense there would be conformal symmetry. I mean, here it's already very special. You have to symmetrize the amplitude, and you have to take the scaling dimension to have this particular value. So it's not clear what's behind this, I think.